In a purely deterministic universe, mathematics is a flawless mirror of reality. If you know the input, your predictor variable, x, you have absolute, infallible knowledge of the output, y. It is a world of perfect, repeating physical actions. Calculate the length of a pendulum, and you know exactly where it will be at any given second. There is no variance. But empirical data rarely behaves this way. In the real world, if you measure two distinct subjects with the exact same input value of x, you will almost always get two slightly different outputs. This chart shows a standard coordinate plane mapping actual observations. The points drift. They scatter above and below where the mathematical relationship implies they should be. Notice how this theoretical line, drawing the cleanest path through the data, actually fails to touch most observations. A rigid deterministic equation breaks down here. To model real-world relationships, we have to build a system that processes probability rather than certainty. To bridge the gap between our theoretical prediction and observed reality, we introduce a mathematical mechanism. We quantify the exact vertical distance from an observed point straight down to the regression line. This distance is the error term, denoted by the Greek letter epsilon. It measures the random deviation of a single data point. By injecting this random deviation into our equation, the dependent variable y changes completely. It is no longer a static result. It becomes a random variable itself. We establish two baseline assumptions about this arrow term. First, if we were to measure the entire population of data, the positive and negative deviations would balance out perfectly. The expected value of epsilon is exactly 0. Second, we assume that this random error possesses a specific amount of spread, a variance, which we denote as sigma squared. With epsilon locked into the model, we stop predicting exact individual outcomes and instead learn to model how these two variables relate to each other on average. This brings up a critical question regarding our second assumption. As we move along the x-axis, testing different predictor values, how does the variance of that error behave? This chart reveals the true shape of the probabilistic model. The regression line acts as an anchor for a series of probability distributions. We analyze the expected outputs at fixed specific intervals along the x-axis, marked here as x1, x2, and x3. For every given x, there is an entire distribution of potential y values. Notice where the peak of each bell curve lands. The mean of each distribution sits perfectly on our deterministic line. Look at the width of these curves. They are identical. The data spreads out from the mean by the exact same amount at x1 as it does at x3. This property is called homoscedasticity. It means the variance, our sigma squared, remains completely stable regardless of where you measure it along the x-axis. If the spread widened or narrowed as x increased, a condition known as heteroscedasticity, our predictive bounds would break down, rendering estimates at the extremes unreliable. The intercept and slope parameters merely dictate the angle and elevation of the center.
It is the variance that dictates the spread of reality around it. This three-dimensional landscape is the true population model of simple linear regression. It maps the topography of probability. That mapping relies on an idealized infinite population, but researchers operate on limited sample observations. Consider a 2009 automotive engineering study examining 14 unique samples of biodiesel fuel. The goal was to predict a sample's cetane number based on its iodine value. When we plot the observations from these 14 samples, we get a finite scatter of data. The challenge is drawing the optimal line through these specific coordinates. We cannot rely on subjective visual guesswork to find the center. We apply a method pioneered by mathematician Carl Friedrich Gauss, the principle of least squares. The objective is to minimize the sum of the squared vertical deviations. If you treat those vertical error brackets as the sides of actual squares, you can visualize the math. As you adjust the angle of Valois, the distance to each point changes, causing the area of each geometric square to grow or shrink. The optimal regression line is the exact objective geometric position where the total combined area of these squares reaches its absolute minimum. Locating that specific minimum area requires precise mathematical derivation. We construct an objective error function that calculates the total squared error based on our slope and intercept estimates. We then isolate the minimum by taking the partial derivatives of this error function with respect to both parameters. Setting those partial derivatives exactly to zero mathematically locks in the global minimum of the function. Running that raw calculus manually for every single data point in a massive dataset is completely computationally exhausting. We rely instead on shortcut summary statistics, denoted as SXX and SXY. These formulas are the algebraic distillation of that calculus. By feeding the basic sums of the sample data into these shortcuts, we calculate the slope and intercept without performing the underlying derivations point by point. Estimators derived through this least squares method are mathematically guaranteed to provide the most objective, unbiased fit possible for your sample data. Applying those shortcut formulas to the 14 biofuel samples locks the least squares regression line into its final, optimized position. We calculate residuals, the physical differences between observed Y values and the line's predicted values. Stripping away data points leaves only these deviations. Thanks to least squares, summing all positive and negative deviations cancels them out perfectly. The total sum is exactly zero. This is the direct sample-level manifestation of the theoretical assumption we made at the very beginning, that the expected value of our error term equals zero. The residuals generated by the least squares fit serve as our best tangible proxy for that invisible theoretical population error. Simple linear regression is a structural compromise. We apply rigid calculus to flawed sample data, successfully extracting a deterministic mathematical signal from inherently probabilistic noise.